constant slope. And we maintain the feeding condition constant, the discharge and the water. And what we observe is, on this picture, different bed states, as defined by Iseya and Ikeda, sorry. Oh, sorry. So, as was defined by Iseya and Ikeda, we observed in this kind of experiments three evolution of three bed states, different bed states, smooth bed, transitional, and congested. To each bed state correspond different transport rates, with a higher transport rate for the smooth bed and a very low transport rate when the bed is totally armored. And associated with this variation of transport of solid transport, we measure a fluctuating bed, slope of the bed with a kind of periodicity, here in this case, 3 hours for each fluctuation of the bed slope, and which vary between 1.5 and 2%. So, now we'll try to explain with a little story how we obtain this kind of fluctuation, and with some videos. So, you can imagine that the bed is now fed with a constant water and solid discharge. And because we have this very efficient trapping, you upgrade the bed by trapping the fine sediment. This is a video you saw before, with the fine sediment being captured between the core surface. And you continue to feed the bed, and you upgrade your bed. After a while, you will obtain a very efficient trapping because the armor is fully developed. This is the same experiment, we didn't change anything. You just wait a few hours, and this is what you obtain, a very efficient trapping. And you cannot see anymore the fine sediment passing in this section.
But it's still being fed.
We don't change anything. You don't change anything. The feeding is still constant.
What's the mixture? It says...
it's a bimodal mixture in this case.
So it's 2.3 and 9 millimeters,
yeah.
Equal amounts?
Yeah.
In mass?
Yeah.
Okay. I don't see any of the fine stuff.
No, because they are trapped very efficiently, because the armor is very well developed. And in this situation, in this configuration, you trap very efficiently the fine sediment.
So they're trapped way upstream?
Yeah.
So you have downstream also?
Yeah. So this is what I illustrated before with my two contrasted effect. We are constructing a very stable slope. If you wait a bit longer, you can imagine that when you feed a canal with the sediment, after a while you will saturate the bed. The slope increase cannot be infinite. After a while, what you inject will necessarily reparticipate to the transport. So you upgrade your bed, you capture the sediment, but after a certain threshold of slope, what you inject necessarily will be transferred. This is what happened in this case. And when this happens, you create two effects. First, you fill the interstice at the bed surface with the fine sediment. This increases the mobility of the core sediment, which in turn impact the other sediment by their velocity. And we also have this weak layer below the core surface, and this is responsible for a strong change in the bed configuration. Look at this video. This is the same than before. A few minutes later, so you see, we could just to. Oh, sorry. So if you look carefully, you will see that some fine sediment will participate again to the transport. You can see the sand here. Actually, the armor layer is being destroyed. You have here the two effects presented in the little drawing, with the fine sediment smoothing the bed and the coarse sediment passing very efficiently over these sediments and impacting the sediment at rest and destroying what was in place. It's a bit long, but it's worth to see the video up to the end. The evolution with more and more fine demand coming from upstream. So actually, what we observe here is that all the fine sediment were captured below the core surface are released in the flow when the local armor is destroyed. All these fine sediment re-participate to transport, and so we come back to the beginning, just to see the change in the bed morphology during this effect. So this is what we call bed load sheet, but I'm not sure, maybe we could discuss this definition, but
when the armor layer is destroyed, is the reach over which it is destroyed, is that limited?
So this is my second postulate, is that this is a multi-scale problem. You can have this locally or over the total length of the face. Well, I lost speed, sorry. So once the armor is destroyed, what you observe is a degrading bed, because this time the armor is totally removed, and the bed can totally erode. Okay. If we wait longer, after a while, once again, you erode your bed, but because you maintain a constant feed, so erosion will not be infinite. The erosion will stop after a while, and you reach a kind of equilibrium with what is injected upstream, and the erosion stops. From this time, you have the formation of clusters because the efficiency of transport diminished, and we start again the erosion process, the aggregating process. So here starts the periodicity you observe in the first slope fluctuation. We restart the phenomenon, and we reconstruct the bed this way by trapping fine sediments. So in this fluctuation, we have exactly two moments where the outlet to the discharge was equal to the inlet to the discharge. It corresponds to two short moments where we have a kind of equilibrium. And in one case, the slope was steep, but with very low transport efficiency. And in the other case, the slope was, after erosion, reduced, but with a very efficient transport efficiency. And what we can show easily using the manual equation, if you consider all the time constant, if you consider that the solid discharge and the flow discharge are constant, this product term efficiency times the slope is constant. This explains why, whatever the experiment we do with a given mixture, so your fluctuation will always be between two given maximum and minimum slopes. I'm sorry, I'm just go fast with that. I'm not sure that I was very convincing with this explanation, but okay, this is what the first postulate. We have two antagonistic effects. The second postulate is that we have a multi-scale phenomenon. Actually, what we observe, the trapping efficiency, the sorting effect, is efficient over finite distances. And if this is repeated in the downstream direction, it means that you can have different parts functioning independently with different bed behavior and slope fluctuations. So this could be simulated with a simple conceptual model representing the bed by different compartments fluctuating in a given slope range. This hypothesis is supported by a simple model, which is here. It's a function including the length of the flume, the different lengths of the different compartments of the bed functioning where the trapping is very efficient, but can be dissociated. With a different period of the bed, this time measured in the experiment, if you use this kind of function, you can reproduce the different scale of fluctuations. I don't want to give detail on this model. It's just to say that we can, with a conceptual model, reproduce the different behavior of the different parts of the bed. And the interest of this is that the compartmentation of the process of grain sorting and bed response can explain that you have different small erosion when, for instance, one part of the bed only is eroding. This is a question you asked Astrid before. The erosion can be very local when you have a local pavement armor destruction. When you have a larger part of the bed, you can have you can have a different scale depending on which part of the bed is concerned by the armor destruction. And the larger erosion concerns the few moments where all the bed was covered by an armor. And this is what, I have a problem with that. This is what is in this picture. With here, for instance, a very large erosion, bed erosion here. Observe when all the bed erodes after a large erosion, armoring process. Another interesting aspect is that actually during the same experiment, you could observe the three processes presented before for the armoring process. We can observe locally the clustering effect with the coarse element being trapped by clusters. Downstream, in the same experiment, it was possible to observe the armoring, local armoring with equilibrium of the transport. And downstream, further downstream, because this one traps sediment and captures the sediment, you can observe some starving effect and another armoring process due to local degradation of the bed. So I will try to do some. I'm sorry, I'm going very fast. I realize now that I have a lot of information for a few small time of presentation. I should have spent more time on this for explanation. So what is in terms of morphodynamics, consequence in terms of morphodynamics? I try to do this exercise, but it's difficult because what you have here is by flume, and the morphodynamics is complicated. You know all that passing from the flume to the field is trying to look by a little hole what is the consequences, what to observe to the large scale, at the large scale, and also maybe something which have a history which can be 1,000 years old. So it's a difficult and non-generous exercise. But anyway, what we define first at the beginning of my presentation is two distance actually. When you go downstream, the sediments are finer, they are more sorted. The coarse sediments are less mobile, and the jam state diminishes. The jam state is the effect of the banks. We can strengthen the armor. So we can imagine that these two distances I presented before change within the downstream direction with the relative importance of the vertical distance, the length, the longitudinal distance, which can increase. This explains why the channel tend to be less armored in the downstream direction, maybe. So I will try to see what are the consequences for the different kind of morphology. So the first situation is when the vertical distance is very large compared to the horizontal distance, which means that the trapping is nearly immediate. You put a mixture in the flow, and the trapping is very efficient. So we talk here about mountain streams close to the production zone or in sediment traps, where finally we have a large difference in grain diameter between the coarse and the fine. We have a strong mobility of the coarse fraction and a strong sediment supply, and of course steep slopes. So here we have a comparison between what we have observed in the field and what we measured in the flume. It's another movie. I invite you to look at on the right, you will have the flume movie. The coarse sediment in blue, the mobility of the blue stones indicates the armor stability. And on the right, you have what could be observed in the field. It's a Hazard-Lewis comparison, but it works to do it. I'll try to look at both videos at the same time. What is that? Okay. I mean, it was my videos. Okay. Before I was supposed to be very concentrated to see that. Okay, see, I will start again the video.
No, go ahead.
Yeah.
You have 5 minutes.
So you have here the feed of the film. You can see this kind of flow, which was at the beginning a kind of sheet flow, very thin layer of water, and after a while it's transformed in a channelization of the deposit. With finally you have some kind of very shallow flow. I will start again because I would like you to look at the sediment deposit in the film. You see that the coarse, the blue sediment protect the deposit in a sort of armor structures, but start to be destabilized by the flow, and we create this kind of erosion. This kind of transport, hyper-concentrated flow transport is also what we observe in the film, and we tend to channelize in the same way, both in both situations. So I have 5 minutes. Okay, so we suppose it's very difficult to say, okay, what we see in the film, this is what is in the field. So we go back to the field and we look what we can observe. So in the field, when you look at the deposit, you observe a very efficient trapping. The armoring is very efficient. So we suppose that what we observe in the film may explain why we have this kind of pulsating nature of transport in the field, but it's difficult to conclude definitely. Another situation is when the vertical trapping effect is the same order as the horizontal distance. So we consider here the mountain streams like the pool, vein beds, with a non-zero sediment supply, large mobility of the coarse fraction, and also maybe fixed bands which can constrain the armor. So we consider here two effects, at the event scale and also at the pluriannual scale. So at the event scale, we think that this process can explain the large fluctuating method fluctuation, like for instance here Gomez measured in a steep slope mountain stream during the armoring process. This is what we measured in the flume with the same kind of experiment. So if you look at the blue stone, you will have also an indication of the armor stability. So here the white sand corresponds to white sediment corresponds to the sand. So here you see that the structure is nearly mobile, but if you wait, you see this kind of pulse of sediment. Here you have an armor nearly stable, but if you wait, you have again this kind of pulse. So this is the two antagonistic effects I presented before. This kind, you can stabilize the bed, but until a limit. After, because you have created this kind of very weak layer below the armor, when it starts to move in, it's very destroying for the armor, nearly stable. And once again, you have this pulse. This is not random fluctuations. You can model that very clearly with a very identified periods, depending on the flow condition we use and the mixture.
So what's varying? That just nothing, or just sort of spontaneously these structures are forming and then going away?
In this experiment, yeah, we maintain a constant feeding and we let the flow. Nothing is changed.
Oh, that's been very chaotic.
So it's finished? I'm supposed to stop?
You're supposed to stop, but keep going for a little.
5 minutes. Okay. So we also think that this phenomenon could be responsible because we have a multi-scale process. we think that